Hey folks, welcome back to the channel. At some point in your programming journey, you might have come across this question, what language should I choose next? Is it Java, Go, or something else entirely? Today I'm sharing my approach and lens on how to choose the right approach to learn languages uh, so that you can be a versatile developer. I would suggest that instead of becoming a Java developer or a Go developer, you should focus on being a language agnostic, versatile developer. But how do you do that? By understanding the paradigms and concepts behind the languages. According to me, you can classify languages into three broad paradigms based on the level of control they offer you. First up, we have low level languages like C, C++, and Rust. These give you a ton of control, and with a lot of control comes great responsibility, right? You are responsible for how you allocate, deallocate memory, and you are responsible for managing lifetimes of objects on the heap. You are responsible for spawning threads and managing thread lifetimes. You care about how you interact with the kernel through system calls and a lot of stuff. You have to think of a lot of stuff. In C++, for instance, we start with raw pointers, right? These pointers give you direct access to memory, but you are responsible for managing the memory life cycle of these objects. This means you'll be manually allocating and deallocating memory on the heap. And with all this responsibility, this approach could be really error prone if not done properly, right? And it can lead to memory leak, segmentation faults, and a lot of unpredictable runtime bugs. To mitigate these issues, C++ has this concept of smart pointers. So these are abstractions which handle memory management, some parts of memory management for you. For example, C++ offers you a unique pointer, which is a RAII based pointer. When you allocate some variable on the stack, it allocates some memory on the heap for you. And as soon as it goes out of scope, it automatically deallocates the memory using the destructor there. There are also things such as shared pointers, which use reference counting. And in this case, you're using some abstraction or a library that is built into C++. And that library handles the allocation and deallocation on your behalf. In case of these low level languages which offer you a lot of control, it's easy to shoot yourself in the foot and cause a lot of unpredictable runtime bugs. That's where Rust comes in. Rust helps you to mitigate these issues with its borrow checker, which catches potential foot guns at compile time. Uh, though progress can be slow when you use languages like Rust with strict rules, but it ensures safety, stability, and performance in your code. Next, we have garbage collected languages like Java, Kotlin, and Go. These languages abstract out some of our responsibilities like memory management and how we do concurrent tasks. They have garbage collector where we offload all the memory management and lifecycle management too, making it easier for us to write concurrent programs without having to worry about low level details. In these languages, memory management is offloaded to a garbage collector which periodically frees up memory that is no longer in use. They also have abstractions for multi-threading, often providing underlying thread pools that allow you to spawn thousands of concurrent tasks effortlessly. Using such languages, the progress is faster and it's easier, and it prevents a lot of foot guns and it prevents you from shooting yourself in the foot by abstracting out and standardizing many of these redundant processes that are used frequently, right? However, the trade-off is performance here because we have some garbage collector and some library code that runs. So the amount of time your code runs will be slightly less because garbage collector has to run in between and some thread pool scheduling logic has to run in between. But you can make progress very quickly while having sufficient performance for the task. Lastly, we have interpreted and dynamically typed languages like JavaScript and Python. These languages allow rapid development by abstracting a lot of details. You don't have to even worry about types. This lack of type enforcement lets you make quick progress, but as your application grows, you might end up with a lot of runtime errors because there's no type safety. Right? That's where TypeScript comes in, which adds type safety to JavaScript, helping you catch some of these errors at compile. To understand how these languages execute, let's talk about compiled and interpreted languages, right? Compiled languages like C++ are translated into machine code before they are run, and CPU executes these instructions directly. This usually results in faster performance because you don't need an interpreter running when your code is also running. On the other hand, interpreted languages like JavaScript and Python are converted into machine code at runtime by an interpreter, which tries its best to figure out the appropriate types on the fly, but this can be slower than pre-compiled code. We also have just-in-time compilers or JIT, which are like an hybrid approach. JIT compilers observe code at runtime, find patterns, and compile frequently executed code in optimized manner by figuring out types of frequently used functions. This can offer a balance between flexibility of interpreted languages and performance of compiled languages. So JIT basically does runtime optimizations of frequently used code. Here's a tip. Choose 3 languages that cover all these paradigms, right? One from the low level paradigm like C++, one from the garbage collected paradigm like Go, and one from the rapid development paradigm like TypeScript. By understanding these paradigms, you can easily extrapolate your knowledge to other languages and become more versatile developer. One thing we can note here while we move through these paradigms is at the low level paradigm, we had a lot of control. And as we move higher to higher level languages like TypeScript, interpreted languages basically, what we see is we are offloading a lot of responsibilities and control to the libraries or the runtime environments. This is because we can't trust humans with coding, right? We will make errors and we will write code that is nasty and which is not optimized. So what developers did is they identified these frequently used patterns and they created these runtime environments and libraries where we can offload these frequently used patterns. Offloading all these responsibilities and control to these runtime libraries ensures that we are using standard approach, which is being maintained by a lot of brilliant programmers, and that ensures us that ensures that we don't shoot ourselves in the foot and cause unpredictable bugs. But that said, learning these higher level languages abstract out a lot of details, right? So you won't know why your app is performing so bad because you don't have that granular control on memory allocation or granular control on how threads are performing, that what is getting more time on the thread. So if you know these lower level concepts, then you can configure these runtime environments so that you can fix all such complex issues that may arise when you have like a large application, right? So I would suggest to learn all the low level paradigms, the paradigms in between like Java, Go, which are garbage collected, and the higher level paradigms as well, and extrapolate all these concepts. And when you know this concept, you'll be like a complete programmer who can configure his app, find these nasty issues because of the low level details of the runtime environment, and you'll have a lot of skill sets that you can extrapolate to new languages that come in or new paradigms that come in. So whatever you learn will not go to waste. That's it for today's video. If you found this helpful, don't forget to like, share, and subscribe, and hang around for more insightful videos like this. Drop a comment below on what languages you're learning and why. Yeah, happy coding, guys. Bye bye.